everybody and welcome to another video. I just wanted to do a really high level overview of the dynamic shared linked libraries for the Linux distribution, the way I see it and the way I interpret it. And what I mean by a very high level is literally not concern ourselves with all of the internals and internal implementation of the DL open, DL sum, and DL close. So how do we eliminate all those complexities in order to understand our code at a very high level if we are not interested in really in-depth technicalities? Um, well, first, you gotta do some reading up on DL open and DL close and DL sum and see what it does, but we can deduce that just by its usage, this is likely to be internally. While DL open is not necessarily a hash table or any sort of data structure, but rather a pointer that points to our opened virtual memory space in that program. We can still look at it as a high level hash table. So because that's what it is internally. I've done some reading on it and it's essentially what it does. And we can also prove that by using Valgrind, where we add more stuff to our shared library file. So essentially how I like to think about it, but after all, the devil is in the details. But once we do DL open, what happens is we create something called a link map, and if you break down the source code of DL open here, you'll see that we are indeed using this structure once we open a file. But before that, if we break down the usage of DL open itself, it is going to sort of let us clear the desk. And with these two lines here that I've added, we're proving that if this shared library is currently active in the current main program, we're just going to increase the reference counter, because that's how DL open is implemented, and DL close. So once you call DL close, you're essentially decrementing that reference counter, and if it drops to 0, you are going to release that piece of memory. But what memory are you releasing? You're releasing the virtual space memory that was created in order to resolve all these symbols. There are many terminologies online, such as symbol table, link map. They're not necessarily the same. They're entirely different things, but yeah, and still it's fun to read about that. So essentially, if our DL file is already open, we are increasing the reference and we are returning the same pointer that was assigned at the beginning, because you're only creating it once. Unless, however, you do something like this, our assertion is going to fail, because we have closed, or will it fail? Well, that's not failing, because it will be opened at the same memory address. Can I force it not to be open at that memory address? 1 second. If I do malloc here and sort of pivot, no. So it will be open the same memory address, but it's not the same file. This is sort of weird anyway. Let me just do this maybe. Nope. Yeah, it would be the same handle all the same. I can probably try to do this, yeah. So yeah, it's the same one, although it's closed. But that's just that just happened to be the case. Or at least I hope so. Let me try to open another one. But the one that doesn't exist. I'll open. Hopefully this, yeah, we finally got there after all. Now it's not opening up at the same memory address, but that's neither here nor there. This is really now can be really confusing. Why is the same address? Well, it's just the way C works. It just found that the next appropriate address would be at the same memory region, so that's just that is some bull jive a little bit. So yeah, it can be confusing, really. Anyway, my point being is, since this is how DLOpen functions, you can think about it as a really high level hash table, and I often remind myself of this in order to make life easier. Okay. Object. Yeah. So here it is. Let's say this is my hash table, and I have new file opened, lib shared. And I'll have my respective symbols in there. And this can also be B2, but these are not resolved straight away. It really depends what your configuration is. So if we think about this high level structure, then now we have cleared all the confusion or all the details behind this. I was gonna say something, of course, in my mind. Oh yeah, it really depends what your options here are. If you use RTDL now, then you're resolving all the symbols at once. But if you're doing lazy, you are not. So we can now see that there is clearly a lot of bytes reachable. That is because once you have multiple references, which means you've increased the reference counter, you need to call it as many references there are via DL close, and this has to be pretty explicitly called because it's C after all. That's why I built the function that goes unload all DL refs, and I would have my DL name and my DL handle. Why is the handle in there? I'm just using DL name. Oh, I'm closing. Okay. So this will do the trick if you don't want to. Well, after all, this has to be explicitly called as well, but it just, really cuts a lot of work if you are not concerned. If you don't want to concern with yourself, if you don't want to concern yourself with keeping track of all the references. You just gotta keep track of one, and then once you're ready to resolve it all, you can go ahead. So what else is there to say? Now, how can we prove that DL symbol, once we do DL symbol, we're doing a hash table lookup internally? Of course, after all of the symbols are loaded in the DL symbol table, and we actually have some access to that data structure. We can prove that by adding more stuff to our DL shared file. So let's say I'm including stbds, and what's really also interesting about this, why is it possible for me to resolve printf? Well, that's because you've included stdio library, standard IO library, and now all of those symbols have become available to you. But let me just comment out the stbds header, and now we can see that we are allocating less bytes on heap, and we can also prove by this that this link map is actually allocated on heap. It uses malloc as well, because Valgrind is able to detect it. If it was using something like mmap or similar, we wouldn't be able to see it with Valgrind. And that's one of those things that really got me confused when I was debugging Python. I wasn't able to see all of the bytes allocated from based on the Valgrind report, and then it turned out that in Python 3 version on Linux platforms, Python is using mmap, which is sort of a native way on. It uses mmap to allocate memory pools, but that's another discussion for another day. Even if you're using memory pools, you still gotta reallocate at some point. It just depends when. Unless you're using your memory pool for just, short integers or something like that. Something that's that you can look up easily, that you don't need to necessarily allocate memory for. So yeah. And also what's worth mentioning, is in the previous video that's titled Compile Time Significance for CREPL. We had two commands for compiling our dynamic shared library, but if you really want to focus on the performance, it is important to note that you don't need to first link it and then compile it, because you can do it in one command, because now one command will be faster. Why is that? Because if you're linking it manually and you're outputting the O file, the object file, that means that you need to write to disk, and the other command will read from disk, and it will need to load it into another buffer while that compiles in order to, have access to it. So if you want to cut to the chase, really, and not have those two potentially expensive operations depending on how large your C file is, just go with in-memory. Well, in-memory linking, where what I mean by that, it's not outputted to the disk, it's not written to the disk, where you have to do a subsequent read. So yeah, that would be also an improvement we could have done in the previous video, but I reckoned that it would be an honorable mention in this video just to get the additional boost. But we really took down the giant in that video as far as the compile times performance and build performance, in other words. But this is just a nice additional touch that you can make in terms of faster compile times overall if there is a huge load of them. So yeah, that's how you can approach DL open. You can just look at it as a huge, well, not really huge, but as a hash table or a map, a link map structure behind the scenes. And what I also like to note is you wouldn't necessarily do DL sum in an expensive loop, because now you have to look it up from the hash table, right? Let's say we have an expensive loop here. And I don't have the utilities to currently time this, but let's hope that it is noticeable. Or not. Maybe 100,000. Yeah, I mean, this kind of stuff is really tough to see. Okay, let's go with this, shall we? 1, 2, okay, 2 seconds. I know it's a really rough way to benchmark it, but my point being is you wouldn't resolve your symbol in an expensive loop. You would move it out of that loop, because now you're repeating operations. Let me just get my two timing functions real quick, and then we can take it from there. I mean, actually, we don't need it, right? I can do time it. Is it this one? Ooh, no, it's just time. It just looks like. So 08, 09, 07. And if that's in the expensive loop, compile it and run it. So now we've gotten the boost in the user section where it's not point, what was it before? Yeah, this is not a really neat way to time it. Anyway, the more acceptable code would be to move your symbols out of the expensive loops and resolve them on their own before you make any expensive calls. So that would be all. Alright, thanks for watching. Until next time, take care.